Hello everyone, I am audible.
Yes, audible.
Okay, thank you. Let me share my screen. So today is going to be NPTEL live session week 2 for the course of Foundation of Cryptography. And so basically I will first discuss the assignments that were posted on NPTEL website for the last 2 weeks, and the results, like the answers are given, but I will just discuss once. And if you have any problem, you may ask. And then we will proceed to this week's problem solving session. So this is week 1 assignment. Question was question 1. This was it was already actually discussed in the last week, if you remember. So which of the following is or are valid conditions for perfectly secure encryption scheme? So as we discussed that the requirement for encryption scheme to be perfectly secure is that the message plain text space distribution should be exactly same to the view of adversary even after seeing a ciphertext of with any underlying plain text in it. So we can say that prior probability of capital M equal to some specific plain text small m should be equal to seeing a ciphertext small c, particular ciphertext, then guessing that which is the underlying message. So the probability that the underlying message is small m, that posterior probability should be equal. So this is the third option, as you can see. This question was also discussed in the last week live session. So given this plain text space probability that plain text is A, that is 0.3, plain text is B is 0.3, and plain text is C is 0.4. So as you can see, the sum of all this probability leads to 1. So which implies that A, B, C are the only plain text available in the plain text space. And then we calculate what is the probability that the ciphertext turns out to be D. So we consider all the 3 disjunct cases that if the message plain text message was A, and then the key of the shift cipher was 3, which means D, if we consider the mapping of each letter starting from A to be A corresponding to 0, B corresponding to 1, like that. So if the key K was D, which is equivalent to value 3, then A would be mapped to the ciphertext D. So like that, we consider all the 3 disjunct cases, and then we get that as the probability of the key being any of the letter chosen uniformly randomly from the alphabet 20, which is the set of 26 letters, so that probability is going to be 1 by 26, and so that's how we get the probability that ciphertext is D is 1 by 26. The next question was which of the following statements is or are necessarily correct? First given is any encryption scheme with key length less than message length cannot be perfectly secure scheme. So as we know, for the perfectly secure scheme, the requirement is that we always XOR the message with the uniformly random key. And of course, for XORing, bitwise XORing, the key length has to be equal to the message length. That is also a drawback of OTP. If you remember, that is an example of perfectly secure scheme. In general, also for any perfectly secure scheme, the key length has to be at least equal to the message length. And the next option, given the one-time pad scheme, the scheme is no longer perfectly secure if on any subsequent invocation of the key generation algorithm, an earlier key gets regenerated. So about this second statement, let's see once that what was the one-time pad scheme. As you can see in the left-hand side, it is just XOR of plain text message M and the key space K. And then we get bitwise XOR of these two and get the ciphertext C. Now, what if, so we know that this K comes from uniformly randomly chosen from the available key space. Now, what if we are repeating this same OTP scheme for various messages, say M1, M2, and so on, and each time key is sampled as a uniformly random sample from key space. And what if that in some ith step of this encryption, we get some ki which is equal to some kj of jth step, where I is not equal to j. So even if ki is equal to kj, the adversary should not know. The adversary has no way to know that in which particular value of I and j the key are going to be same. If the adversary would know the information that particularly after this point of time we will get the ciphertext which is encryption of message M with the same key ki, in that case the adversary would have calculated C1s or C2, sorry, Ci's or Cj, and would get the value of Mi's or Mj. But adversary cannot learn this thing because all the ki are generated uniformly randomly. So even if there is repetition in some particular step, the which step this regeneration is happening, that is not known to the adversary. So this is not a threat to the security of OTP, which is a perfectly secure system. So that's how we say that the second statement given here is not correct. So among these two, only one is the correct statement, that key length should not be less than message length in a perfectly secure scheme. Okay. And there was another question: a malicious adversary is best modeled in which of the following adversarial models? So if you remember, in the last week also we discussed in brief that the power of adversary can vary in several attack models. So just for your information, we will reiterate this thing. So the adversary, when it is least powerful, is the ciphertext only attack model, where the adversary is just an eavesdropper and it can observe the communication channel and see the ciphertext only. And it does not have any information about the underlying message for any of the ciphertext. And what is the notion of security for a EAV secure crypto system that is secure against an eavesdropper? That crypto system should ensure that adversary should not be able to gain any extra information about the distribution of underlying message by looking at the given ciphertext. So here the adversary has least power. It just can see the ciphertext, nothing else. Then comes the KPA model, or known plaintext attack model. Here adversary has got access, you can assume, to a table which stores some plaintext ciphertext pair of values. But which plaintext and ciphertext pair value should be contained in that table, that information cannot be controlled by the adversary. So basically, this is just somehow it manages to get access of plaintext ciphertext pair, but it cannot control that for which plaintext it wants to know the ciphertext, or for which ciphertext it wants to know the plaintext. So, but it is still the adversary is more powerful than the COA, right? And then comes the CPA security model, so chosen plaintext attack. Here adversary has access to an encryption oracle such that it can see corresponding ciphertext of any plaintext of its choice, and it can query the oracle any polynomial number of times. And provided that access to encryption oracle, the CPA secure crypto system ensures that adversary should not be able to effectively distinguish ciphertext of a plaintext M0 from ciphertext of another plaintext M1, even after having an access to this encryption oracle. And this pre-challenge and post-challenge query phase means that first the adversary can access the encryption oracle to get ciphertext of its choice of plain text. And this query phase is before the challenge phase, so we call it pre-challenge query phase. And then comes the challenge phase, where the adversary provides two messages M0 and M1 of its choice, and in response it sees the ciphertext of any one of these two messages. We call it the if some verifier chooses the bit B to be 0 or 1, any one between them, and we call that verifier encrypts MB and sends back to the adversary, and adversary does not know what the value of B is. Its task is to guess the value of B, and a CPA secure crypto system ensures that the probability that adversary guesses the bit B correctly, that probability is negligible. And then comes the CCA secure system, where it is chosen ciphertext attack model, and this is the model where the adversary has got the most power. And here basically, apart from having access to an encryption oracle, the adversary also has access to an decryption oracle. So apart from getting to see the corresponding ciphertext of any plaintext of his choice, the adversary can also see any underlying plaintext of its ciphertext chosen by itself. So, but there is one restriction, that in the post-challenge query phase, for the decryption oracle query, it cannot submit the challenge ciphertext itself. Otherwise, the adversary would trivially win. So, with that restriction, the CCA secure crypto system ensures that still, with the access of encryption and decryption oracle, the adversary should not be effectively able to distinguish between encryption of M0 and encryption of M1 with non-negligible probability. So that's how we can see that the most powerful adversary we model is in the CCA model. So the previous question's answer goes to CCA. Then there was another question. Assume that you are given a 300 character encrypted message encrypted in Visioneer crypto system, in which you know the plaintext word cryptography occurs exactly 2 times, and you know that the ciphertext sequence, this given sequence is the encryption of cryptography. So with these informations provided, you are observing that the first occurrence of this sequence of like encrypted sequence of cryptography, GTMJ and so on, this thing starts at character position 18, and then second at character position 246. And from this information, how do you know that what was the key length of the key used for encryption? So let's see this illustration. You have been given this some text, and in the text there is presence of the string cryptography twice, and in the ciphertext you can see the same sequence iterated at exactly same position. So the first occurrence of G corresponding to this letter C occurs at 18, and the second occurrence is at position 246. Now what it implies is that for whatever be the length L of the key of this cipher, so this L times repetition, that should be completed within this period. So this gap 246, the gap between 246 and 18, this should be a multiple of the key length, right? Otherwise, the C should be encrypted with some other ki value other than k1. So this is ensured only if the whole difference is divisible by the length L. So that's how we conclude that the length of the key is 6, because among the given option only 6 divides the quantity 246 minus 18, which is 228. So we conclude that the length of the key is 6. Week 2 assignment. So the first question was, let G be a secure PRG, then which of the following is or are not a secure PRG? If you remember from the last week's session, we discussed actually the first three security of these first three construction of proposed construction of PRG, and we analyzed their security. As so, the fourth one was not there in last week's session, so we will just cover that. The seed of a PRG being uniformly random over the seed space. So this S, any seed S, is a uniformly randomly chosen value from the seed space, right? So the probability that parity bit X of the seed S is 0 or 1 happens with exact probability half. Okay. So that's how the, even though you concatenate GS with some fixed value X, and this value is the parity bit of S, so that is nothing, like no different than putting a random bit choosing from the space 0 and 1. So, and already GS is a secure, so the output string of GS is not distinguishable from a uniform random string from the same space. So that's how we conclude that GS concatenated with X is not indistinguishable from a uniformly random string. So G4S is a secure cipher, and rest of the three are not, because if you recall, because seeing the output GS concatenated with S, you can parse the output because you know the input length and the output length. So you know, seeing the output string, which part is belonging to the seed S and which part belongs to the value of GS, and then you can just check that, being G is a public deterministic algorithm, you can just check if the applying G on the last part of the string produces the first part of the string, and that's how you can just simply distinguish this from uniform random string. And similarly for the second construction, the output strings first half is exactly same as the output string of the second half of the output string. First half of the output string is exactly same as second half of the output string. That's how you can distinguish this from uniform random string. And the third option also, XORing GS with GS itself always produces 0. So you can always see the output to be 0. Okay. Yes, the recording is getting done. We actually, as TA of this course, we are providing YouTube link to the NPTEL authority. Okay, so that link is there. If you want, I can actually at the end of today's session, I can share the YouTube link with you in this chat. But anyway, I think it is supposed to be given to you, who are the attendees of this course, by the NPTEL authority itself. They should mail them to you. I think they will do that. Okay, so just wait for a few days, and just remind me once I can share the YouTube link for my last week's session in this Zoom chat. Okay. Okay. So proceeding to the next question. Which of the following is or are true about PRG? So given that PRG is a deterministic algorithm, which is of course true, and so PRG is not a randomized algorithm, so next option is wrong. We can construct a PRG which is secure against a computationally unbounded adversary, which is wrong, because if you just exhaust the whole key space of a PRG, then you can surely obtain what is the exact seed by seeing the output of the PRG. So it is not possible to construct a PRG which is secure against a computationally unbounded adversary, only because that say the seed length of the seed is L, the bit length of the seed is L, then doing 2 to the power L exhaustive search on the seed space is not allowed by a polynomially bounded adversary. So in computational secrecy model, we always talk about some probabilistic polynomial time adversary. So its runtimes is bounded to be polynomial. So that's how PRJ is secured against polynomial time adversary, not against computationally unbounded adversary. And same seed can be reused. That is also not true. So every time if you use the same seed, then the G of S will be same, right? Okay. Which of the following is or are negligible function? So okay, let's look at it into detail. So if delta n is a negligible function, then for any positive polynomial fn, there exists an n naught belonging to this natural number set, so that for all n greater than n naught, delta n is less than 1 by fn. Okay, that is the definition for a function to be negligible. Now, just examining these given options, 1 was 10 to the power minus root n. So if we assume that there exists some polynomial with degree k, so let's denote it as n to the power k to be that polynomial. And if we just provide in this given delta n less than 1 by fn, we replace delta n with 1 by 2 to the power root n. And taking log in both sides, we get this that k should be less than root n log 3 by log n. This relation we can get. And now for any value of k, we can get some value n naught from this relation, so that for all value of n greater than n naught, this condition is satisfied. So basically, yes, of course, 3 to the power minus root n is a negligible function. And similarly, you can argue for the third and fourth option, which is log n to the power minus log n and n to the power minus log n. Both of them will be such that for any polynomial, positive polynomial, any positive polynomial you take, and you will get some n naught, such that for all natural number n greater than n naught, this function will be less than 1 by that polynomial function. So only exception is the second option. How? Because if you just take 1 by n to the power p by 2 into q by 5, and this will be always greater than this another polynomial. So it's not true for every positive polynomial fn delta n will be less than 1 by fn. So this is not true. Okay, so this is a counter example of such positive polynomial which is less than this given function. So this is not a negligible function. Okay. So here is another question. Difference between perfect security and semantic security involves one or more of the following. So in the respective indistinguishability experiment, adversary has the exact same probability of success. Of course not. In perfect security, we say that in the indistinguishability experiment, the adversaries can win always probability exactly half. So it has nothing to do apart from randomly guessing the underlying plain text. Okay, like given a ciphertext which can be encryption of either M0 or M1, guessing which one is the encrypted underlying message, actually that probability that guessing can be only done by random guessing by the adversary. So for perfect security case, that probability of winning is exactly half. But for semantic security, when we consider in the computational secrecy model, that becomes half plus some negligible function. Second statement is that bounds on how long the adversary can run the experiment. So as you know, perfect security is achieved against unbounded adversary. So adversary can run unbounded time, but in semantic security, we always define our crypto system secured against polynomial time adversaries. And also bounds on the computational capabilities of the adversary. Yes, so computational capabilities is also bounded in case of semantic security, but not in case of perfect security. So the second and third statements are correct. This is the last question of week 2 assignment. So it was let CS of S and R. Okay, so whenever this Zoom meeting ends, as I said in the last session also, so you please join in the same link again when this meeting ends automatically. Okay. So let CS of S comma R. So CS is some function which takes as input some string S and some random number R, where S is an n-bit binary string. Then we say that this is a function defined as cyclic shift of string S by R bits. Also define a construction G of S equal to CS of S R1 concatenated with CS of S R2. So you basically shift the string S by R1 bits and then concatenate with it shift by R2 bits of the same string S. Okay. Now there are some options given. First is, since the security of CS of S and S comma R is not known, security of GS cannot be determined. So first thing is that the CS of S comma R is not a PRG at all, because for input S of length n and for input R of some unknown length, it just returns back a n length output string. So there is no expansion, and this is no way like the question of security is not there at all for CS of S and R. It's just a function, so we cannot comment on the security of proposed PRG-GS by looking at this. And the next option is GS is necessarily a PRG. So we can analyze whether this is PRG or not. So let's see here. As you can see that these two halves of GS, so output of GS is of length 2n, and first half of this output string must be some bits of shift of the second string, because both of them are just nothing but cyclic shift of string S by different amount. So of course, the two halves of GS, this output will have shift distance of R1 minus R2 mod N, right? So this is very obvious, and using this only, any adversary or any distinguisher can effectively distinguish the output of GS from any uniformly random string of length 2n with non-negligible probability. So as we were saying that whenever the first verifier tosses a coin to decide whether it will provide the adversary with output of PRG or with a uniformly random string. If B is 0, it decides to provide adversary with the output of GS, which is CS of S comma R1 concatenated with CS of S comma R2. And if B is 1, then Y is, okay, this will be 2n, not n. This is a small mistake. So because the output of GS is of length 2n, so if B is 1, then it will provide the adversary with a uniformly random string of length 2n. And now what adversary does is that it parts Y into Y1 and Y2 such that each half has length n, and it check if shifting Y produces Y2 by some R number of shifts, where R has to be between 0 to n minus 1, because after that it will be just repeating the sequence. So if Y1 is a cyclic shift of Y2, then it has to be found by doing at most n minus 1 number of cyclic shift on Y1. So if it is true that Y1 is a cyclic shift of Y2, then it returns B dash is 0. B dash is the adversary is trying to guess that whether it has seen the output of a PRG or it has seen uniformly random string. So then it returns B dash equal to 0 or it returns B dash equal to 1. Now, what is the distinguishing advantage of this adversary? So we analyze that if the bit B chosen by the verifier was actually 0, then of course the adversary will find Y1 to be a cyclic shift of Y2 and it will output B dash equal to 0. So that probability that B dash equal to 0 upon b was actually 0, that thing is always 1. And next comes if b was 1, so verifier actually chose to provide uniform random string to the adversary. Then what is the probability that the adversary found y1 to be a cyclic shift of y2 in a uniformly random string of length 2n? And that probability, if you analyze, so in a the total number of 2n length string is 2 to the power 2n, and then the second half of the string can be any cyclic shift of the first half of the string, and first half of the string can have 2 to the power n number of combination, and for each of them for n number of cyclic shift, n possible string will be there. So that's how we get in the numerator n into 2 to the power n, and the distinguishing advantage becomes 1 minus n into 2 to the power n by 2 to the power n, and which is of course not a negligible quantity. And that's how we conclude that as adversary is able to distinguish the output of the proposed construction of PRG G from any uniform random output of length 2n. So this is not a secure PRG. So among the provided options, of course, the third option is the only correct option, that efficient adversary can distinguish between GS and a truly random generator with more than negligible probability. Now we come to the problem solving session of this week actually. So first question is, select the incorrect options from the following. Stream ciphers are deterministic. Stream ciphers are randomized. Same key can be used for encrypting multiple messages in stream cipher. Stream ciphers are single message CPA secure. So anyone would like to answer? Which are the incorrect options? Okay. So basically all the okay. No, they have said incorrect option. So yes, 2 is incorrect, you are correct, but the other options like 3 and 4 are also incorrect. Okay, so stream ciphers are deterministic, that is known to us, so it is not randomized. And same key can be used for encrypting multiple messages in stream cipher. No, it cannot be used because so for the same seed, g of k will be same again and again, so we cannot use it. And stream ciphers are single message. Just eavesdrop stream cipher are secure only in the presence of eavesdropper, so it is EAV secure. It is not CPA secure. Okay. Okay. So this is a question about again one-time pad and both CPA security and multi-message security also. So one-time pad is multi-message secure in presence of eavesdropper. One-time pad is multi-message secure under CPA attack. One-time pad is single message secure in presence of an eavesdropper, and one-time pad is single message secure under CPA attack. Anyone would like to answer? This meeting is going to end actually. You can join again in the same link when it ends. And anyone would like to answer, then you can just unmute yourself because there are very few participants in this meeting. Anyone answer? What is the meaning of multi-message? Okay. So whenever you say you have fixed some key k, basically you can query that just We were talking about what is multi-message. So consider the game between adversary and a verifier. Okay. So let's say adversary gives like if we consider just the eavesdropping situation, so where the adversary is just an eavesdropper to the communication channel, there is no game basically, it just observes the ciphertext on the channel. So considering that case, if whenever the encryptor, whoever is sending the message, sends the ciphertext in batch, so say there are some L number of messages which are getting encrypted on the side of encryptor, and all this L number of ciphertext are getting communicated through the channel at once, at a time. Okay. So then the eavesdropper is able to see all the L encryptions which might have been done using same key for all the messages. So if it is if all the messages are getting encrypted one after another as different sessions, then maybe different key are getting used for each of the encryption of the messages. So say there are some Q number of messages getting encrypted. So first adversary sees in the channel the encryption of M1, and maybe encryption of M1 was getting done by using some key K1. And then in the next session, it sees the ciphertext C2, which is encryption of M2 using some other key K2, uniformly randomly chosen key. So that is a different case which we consider in the single message security. But when we say multi-message security, then it means that the eavesdropper or the adversary is able to see all the Q number of encryptions C1, C2 to CQ at once, and all of them have been encrypted from M1, M2 to MQ by using the same key K. So that is how we consider the situation of multi-message security. Okay. That is the scenario of multi-message thing. Okay. Now, in case of one-time pad, let's think about this question particularly. So in case of one-time pad, we already know that it is single message secure in presence of eavesdropper, or OTP is EAV secure, that is already known. And is it multi-message EAV secure? The answer is no. The reason is just as I was saying just now, that if all the message Q number of messages are getting encrypted with same key K in a session, so all the C1, C2 to CQ, so take any CI and CJ among them and you XOR them and you get MI XOR MJ, because the key K is same for all of them. So it is not multi-message secure. The information about plain text are getting leaked in this case. Okay. So this is not multi-message secure against an eavesdropper. And the CPA, of course, in case of OTP, we don't even consider the scenario when the adversary is more powerful and has an access to encryption oracle. One-time pad is only just against eavesdropper adversary. Okay. So the only correct option here is that OTP is single message EAV secure. Hope that clears your doubt. We were asked the question. So proceeding to the next problem. Select the correct option from the following. Single message EAV security implies multi-message EAV security. Single message CPA security implies multi-message CPA security. Multi-message EAV security implies single message EAV security, and multi-message CPA security implies single message CPA security. Anyone would like to answer which are the correct options among the following?
I think fourth one looks correct.
Fourth one.
Like
any other correct option? Three is also correct, right? So basically, any scheme, if it is multi-message secure, then obviously it has to be individually single message secure also. And apart from that, actually that option 2 is also correct. Single message security actually implies multi-message CPU security. Any encryption scheme you design to be CPU secured against CPA secure in single message scenario, it will automatically belongs to or automatically achieves multi-message CPA security. But this is not true for EAB security, and the reason we just saw for the OTP case, which is EAB secure for single message, but not EAB secure for multi-message. But for CPA security, once you achieve CPA security for a crypto system for single message, that automatically gives multi-message CPA security. So, yes. Then select the correct options from the following. Multi-message security requires encryption algorithm to be randomized for a stateless encryption scheme. And encryption scheme having deterministic encryption algorithm can be multi-message secured in presence of eavesdropper if it is a stateful encryption scheme. Decryption algorithm in an encryption scheme can be randomized. None of the above. Any answer?
Yes, I think the decryption algorithm has should not be randomized in
Right.
an encryption scheme.
Yes. No, you can
Yeah.
randomize the encryption algorithm, but never the decryption algorithm. And what about the first two options? Okay, so basically, the correct options are first one, like multi-message security requires encryption algorithm to be randomized for a stateless encryption scheme. So basically, whenever we say that the encryption scheme is stateless, so for any message MIMJ, the encryption process is independent of each other, independent of the ciphertext produced by the previous encryption on the previous message block. So in such stateless encryption scheme, we require the encryption algorithm to be randomized in order to ensure multi-message security. And then it is also true that if it is a stateful encryption scheme, then it is possible to have deterministic algorithm and still achieving multi-message security in presence of eavesdropper. So basically, all three are correct. Okay. So let us consider the following notations. Let's say func mn denote the set of all functions mapping m bit string to n bit string. So comment on the size of each of the above set. So first let's think about the first set here, func mn. So what will be the size of the, like what will be the number of all functions possible which maps m bit string to n bit string? So let's think about it as a table. So any function f belonging to this set will have a say lookup table structure. So there is 2 to the power m possible inputs to function f, and for each such input you will have an output which is of length n. So if we consider what is the size of the lookup table for that function, so basically that will be 2 to the power m into n, because each row corresponding to each input to the function will contain n bit output, and then there will be total 2 to the power m rows corresponding to 2 to the power m possible input to the function f. So there will be total 2 to the power m into n number of bits present in the lookup table of function f. And now how many such lookup table is possible? As there are 2 to the power m into n number of bits, we basically get 2 to the power n into 2 to the power n number of such possible table. Okay, so that's how we calculate the size of this set of all possible functions of mapping in bit string to bit string. Now consider the similar thing, permutation n, PERM n. This denotes the set of all permutation on n bit string. So anyone wants to comment on how we like just keeping in view how we calculated the size of func mn, how can we calculate the size of perm n? So permutation differs in just one way, that the input and output length is same. So n bit string gets output to n bit string only, and the output is nothing but one of the permutation of all the numbers, like all the input string. It just permutates the inputs. So in other way, we can say it is just a bijection, 1 to 1 and onto. What will be the size of this? So the answer is also given, so maybe I can just discuss. So let's say if you are filling up the first row of the table, then you have all the 2 to the power n possible string available to you. So you can fill the first row with 2 to the power n possible strings. And then once that is done, in the second row, you are left with just 2 to the power n minus 1 number of choices, because it is 1 to 1. So you can't repeat the same value to be filled to fill up the second row. So like that, continuing, you have the number of choices while filling up the row one by one. You get 2 to the power n into 2 to the power n minus 1 into 2 to the power n minus 2, and so on till 1. So that gives us 2 to the power n factorial. And when we consider fkmn, which is the set of all keyed function mapping m bit string to n bit string, then the key here is the key factor basically. So varying the key k will give you different functions. So the key here itself determines a fixed lookup table for the member function of this set fkmn. So the size of the key, the size of the key space is the size of the set fkmn basically. So that's how it is 2 to the power size of k, or length of the key k. And the similar argument goes for the permutation also, the set of all keyed permutation on input string. Okay, proceeding to the next question. So this is a question on LFSR, linear feedback shift register. So assume a degree 6 LFSR with C0 and C5 equal to 1. If you remember what linear feedback shift register is, so it is like usually in standard LFSR, the output bit is just the rightmost bit of the register. At each iteration, you just output the rightmost bit of the register, and in the leftmost bit, the new value which is entered is some subset XOR of the present value of the register. So here the coefficients are given, feedback coefficients, that the first and last coefficient are 1 only, and the rest of the coefficients are 0. So what are the first 10 bits which are output by this LFSR, considering the initial state to be all ones? This is just a very easy question. We will just see it. So all 1 is the initial sequence, and then you, in the next step, you output the rightmost bit, that is 1, and the input bit is the XOR of first and last bit of the present state of the register. So that is 1 and 1, you XOR them and get 0, and you input this at the leftmost bit in the next step. Then in the next step, you again output this rightmost bit as 1, and you get XOR of 1 and 0, and input into the leftmost bit. So like that it just goes on, and you get the sequence like that. I'll just stop for a while. You can check the sequence of state changes in the LFSR. Just pause for 1 minute and then discuss the next part. I think this is okay. So next part was that is this LFSR maximum length. So the feedback polynomial in the LFSR can be written in this form, that which one of the bit are 1. So among the 6 bit, the first and 6th bits are 1 and rest of them are 0. So that's why x to the power 6 for the 6th bit being 1, and x to the power 1 is also present in the feedback polynomial, and then the constant term 1 is there. So this is how the feedback polynomial is formed, and you check that if it is a primitive over Galois field of 2. And if it is, then we say that yes, LFSR is having 2 to the power 6, like the degree of the polynomial, that is 2 to the power 6 minus 1 number of distinct state sequence, and so it is a maximum length. So, we exclude the all zero state, because once the LFSR reaches the all zero state, then any subset of the present bit you sort, you will always get 0. So the 0 state can never be changed. So we avoid this 0 state, and whenever any LFSR having 2 to the power n minus 1 number of distinct states for n degree LFSR, we say it is a maximum length LFSR. Okay. So in this question, we consider a nonlinear combination generator. So as I said in the previous question, that the output bit is just the rightmost bit of the present bit sequence of the LFSR. But here we consider that the output bit is not just the rightmost bit, rather we will apply some nonlinear function g on the present bit sequence or present bits of the shift register, and we output g of s0 to sn minus 1 as the output bit. Also, we assume that feedback coefficient of the LFSR are known, but its initial state is not. And then you have to show each of the following choices of G does not yield a good pseudorandom generator. So how do we show that? Any idea? So the first one is said that G of S0 to Sn minus 1, which are basically the bits of the n degree LFSR. First bit denoted as S0 and last bit denoted as S minus 1. And at each step, you output S0 ANDed with S1. This is bit just and between 2 bits, S0 and S1. And this is the output at each step of the LFSR. So how it should not be a secure practical instantiation of PRC. Any comment on that? How this nonlinear function G hampers the security of the proposed construction. Basically, what you need to find out is that the what we expect is that at each step the output bit should be uniformly random or indistinguishable from uniform random choice of bits, right? But does this S0 and S1 combination produces a uniform random bit? Even if suppose S0 and S1 are uniformly random individually, S0 and S1, is it uniform random? does S0 and S1 outputs bit 0 and 1 with equal probability? Think like that. Okay. So basically, if you see the simple two input AND table, Boolean AND function table, so S0 and S1, this returns 0 in 3 out of 4 cases. So if you consider the combination 0, 0, 0, 1, 1, 0, 1, 1, value of S0 and S1. So in 3 cases out of the 4 cases, it returns 0. So this condition, like this output is 0 and S1, output 0 with significantly large probability. So it, of course, nowhere nearer to producing 0 and 1 bits with equal probability, right? So it is, of course, distinguishable from a uniformly random output. Okay. And then comes the second one. This is a bit tricky. So if you are outputting S0 and S1 XORed with S2, this is how you output at each step of the LFSR. So how you prove that this is not indistinguishable from a truly random? Okay, so anyone would like to think on that? Maybe like to just give a hint, you can think of what if S1 is 0. You assume that S1 is 0. Then what happens to the sequence of output bits that you get one after another? So basically, in any PRG, the adversary is allowed to see any polynomial number of output bit sequence, right? So you are allowed to see some polynomial number of output bits, and then you can try to guess whether you are seeing output bits from a PRG or from a truly random generator. So just assume that S1 is 0. Then what happens? Then if we consider the output in the first step, S0 and S1, we assume S1 to be 0. Then this AND gives us 0, and 0 XORed with the bit S2 gives S2 only, right? It becomes like OTP cipher. Not really, because OTP cipher is also said to be perfectly secure, right? So I think these two are not really related. I mean, okay, let's see the analysis. So if S1 is 0, S0 and S1 is obviously 0, and 0 XORed with S2 gives you S2. So whenever you see the first output bit, let's denote it as Y1. So Y1 is equal to S2. So you have successfully retrieved one bit of the initial state. Your initial state was not known initially. What is the initial state of the LFSR? That was not known as per the question. But just assuming that if S1 is 0, then you can see that the output Y is nothing but S2. Now let's proceed even further. So what happens is that in the next output bit, Y1 is basically S1 and S2 XORed with S3, right? So you shift, at each step you shift one bit position. So that's how S0 that's how you just get in the Y1, you get S1 and S2 XORed with S3. Again, S1 is 0 as we assumed initially. So this is 0, and 0 XORed with S3, you get back S3. So whatever you see in the output bit, that gives you the information about initial bit sequence one after another. And then in the third step, Y2 is basically S2 XORed with S3, S2 ANDed with S3 XORed with S4. And you already know the bit S2 and S3. Okay. So if you know this S2 and S3, you know end of them, and you are also seeing Y2. So you can recover S4, right? You just see Y2 and again XOR with Y2, S2 and S3. So you get back S4. S4 is also retrieved. So one by one, all the bits of the initial sequence are getting retrieved. And then like that in the fourth step, with the knowledge of S3 and S4, you can recover S5. Thus n minus 1 bit, okay, actually it will be n minus 2 bit. So we are assuming S1 equal to 0. We don't know about S0, okay? So we are assuming S1 equal to 0, and then you just assume there will be two cases for S0. S0 can be 0 and S0 can be 1. So there are possible sequence of S0 is 0, S1 is 0, and then you retrieve all the sequence S2, S3, S4 to Sn minus 1. And another possibility is S0 is 1, and then you assume S1 to be 0, and then you get back S2, S3 to Sn minus 1. So this much, with this much information, if you are again continue to observe the next output bits, you can just distinguish whether this output you are seeing is from a PRG or it is of uniformly random. If it is uniformly random, then of course any bit S1, S2, S3, you can't guess anything about this value, right? So that's how you can distinguish between this proposed practical instantiation of PRG of like this LFSR and truly random generator. So that's how it is not a secure construction of PRG or secure construction of LFSR. Okay. Coming to again, this is a MCQ question. Which of the following is or are true for one wave function? OWF is deterministic function, OWF is randomized function. Any many-to-one function can act as OWF. OWFs are necessarily injective function. Okay, the answer was already given. Sorry for that. So OW is a deterministic function. Anyone has any question about the other options? Why they are false or something? One-way function, what do we mean by one-way function? Let's just recap once. So one-way function is a function for which, given any input x, you can efficiently compute fx. Efficiently means in polynomial time, you can compute fx given x. But 1 and 3, true, it was okay. They wanted to know which are the true option. We were saying 1, 3. OW is deterministic, that is true, okay. Any many-to-one function cannot act as OW wave. So one very trivial example could be, you know, okay, again just to if this meeting ends, just joining the next in the same loop even. So we were saying that any many-to-one function cannot act as OWA. Trivial example can be, you consider the function, say, f of x comma y equal to xy. So this was also discussed in the lecture, NPTEL video lecture itself. So xy is a many to one function, right? So you consider, say, the output 30. So 6 into 5 can produce 30, 10 into 3 can produce 30. So there are many possible combination of inputs which can give you 30 in the output. So that is essentially many to one function, but it is not OWF. OWF requires that given output of any uniformly random input, so given some y in the output domain, you can find a pre-image of y with negligible probability. So you can guess some value x dash, and the verifier will check if f of x dash is equal to y, and the probability that you win in this game is negligible. That is the requirement of function to be OWF, and existence of such function is not yet known, but we believe upon existence of such OWF and construct crypto primitives. So any many to one function cannot act as OWF because f of xy equal to xy is not a OWF, and that is described in quite detail in the video. Basically, if xy is even, then you can just divide it by 2 and output like as pre-image of xy, you can output xy by 2 comma 2, and that is a valid answer. That is a valid pre-image of xy. So that's how you can guess the pre-image of any xy with significant probability. So it is not OWF. Okay, basically to prove some statement is wrong, I think one counter example is enough to prove that. You can, I believe you can find like quite a lot of them if you just think on yourself for some time. Okay. Uh, so proceeding to the next question. Which of the following candidates is or are not necessarily secure PRFs? In all the following options, you assume FKX is which like with key space n-bit binary string and input space n-bit binary string, and output space is also n-bit binary string. So it is a length preserving PRF, and it is also given that FKX is a secure PRF. Now they have proposed some construction of other PRFs. You have to tell whether they are secure or not. We will consider them one by one. So you can just here they are given as S. You can just replace them as K. Okay, just consider them as typo. We are denoting the key as K here. So does not matter. Just consider this GKX equal to 1 concatenated with FKX, and GKX is f of x with key as f of kx. So these are 4 proposed instantiation of PRFs. So anyone want to comment? Let's first consider the first one. GKX equal to FKX XORed with FK of X bar. X bar is just one's complement of the binary string X. So any comment on the security of GKX? I'll think for a few minutes. Let's talk on it. Okay, so let's first proceed with the first instantiation. Let's see. There is a verifier and an adversary, as we know. The security games occurs in case of PRF. So what verifier does is that it chooses to either output a PRF output. So it runs the function f dash with key k on the out on the input query coming from the adversary. It can either choose to provide output based on that PRF computation, or it can choose to output just a truly random function output. So we denote here by T truly random function. Okay. So now the adversary can submit any query input x1, and the verifier will output y1. Okay. Now to the adversary's job is to somehow spend polynomial number of time. That's how it can submit actually polynomial number of query input and see its output and guess and use that information to guess what was the bit B chosen by the verifier. That is whether the verifier uh, outputs to it a PRF output or a TRF output, truly random output. So the adversary's job is to guess B, and it outputs a distinguishing bit B. Adversary wins if it is able to correctly output B dash equal to B, otherwise it loses. So here, to distinguish fk dash x from truly random function's output, what adversary can do is that it can first query with some arbitrary x1 of the input space and see its output y1. And then in the next query, it queries with input x2 such that x2 is 1's complement of x1, x1 bar. And it also sees the output y2. Now it just checks if y1 is equal to y2, because as the adversary submitted x1 and x1 bar in the consecutive queries, and so y must be uh, exactly same for all these two cases, right? So first case fk of x1 XORed with fk of x1 bar, and in the second case fk of x1 bar XORed with fk of bar of x1 bar, which is again x1. So this is essentially is going to be the same. So the adversary checks if y1 is equal to. If yes, then it returns b dash equal to 0, which means b dash equal to 0 is returned by adversary, means that adversary is saying that okay, the verifier gave me a PRF output uh, as y1 or y2. Else it returns b dash equal to 1. Adversary says b dash equal to 1 means that adversary is saying that I was seeing truly random output till now. Now let's see what is the distinguishing advantage of the adversary here. So we calculate the probability that b dash is 0 provided b was actually 0. So provided verifier actually chose the bit b to be 0, or it actually provided PRF output to the adversary, and adversary correctly distinguished it to be a PRF output, that is always 1. Because this y1 is equal to, always is going to be equal to y2 if the y was produced in PRF way. And in the other case, if the y was produced in truly random generated way, then what so as we were telling that what is the probability that B was 1, that is the verifier output uniformly random string, and adversary took it to be a output of PRF wrongly. So what is the probability? That will happen if, so the output is n-bit string, and y1 equal to y2 will happen in just one choice of y2. So that is 1 by 2 to the power n. So the distinguishing advantage is 1 minus 1 by 2 to the power n, and hence we conclude that fk dash is not secure. Ignore this line. This is wrongly has come to this image. Okay. Okay. I hope this is clear. The next construction of PRF is given as gk of x is fk of x concatenated with fk of x bar. Previous one XOR of fkx and fkx bar, and this is concatenation of fkx, concatenation of fkx bar to fkx. So can you comment on this second construction based on as you just saw in the analysis of first PRF construction? Anyone? Okay, so let's analyze the second question. So this is concatenation of fkx bar with fkx. So what happens is that you see that the output of fk dash is actually 2n bit output string, and again the game between verifier and the distinguisher remains the same. Verifier chooses some random bit b, and if b is 0, then it outputs y in this form of fkx concatenated with fkx bar, and otherwise it just outputs truly random output. And what distinguisher can do is that it first submits a input query of the form all 0. So 0 to the power n means n bit binary string with all 0. And it observes the output y1. Okay. Then in the next query, it submits as query input n bit binary string of all 1, and then it sees the corresponding output y2. And to decide whether the outputs it is seeing is actually from a PRF or from a TRF, truly random function, it parses y1 into two half, y11 and y12, and y2 also is parsed into two equal half, y21 and y22, and then it checks if y11 is equal to y22 and y12 is equal to y21. What I essentially mean is that if x is all 0 in the first case, then y1 is fk of 0 to the power n concatenated with fk of 1 to the power n. And in the second case, y2 is fk of 1 to the power n concatenated with fk of 0 to the power n. So fk of 0 to the power n in the second case and fk of 0 to the power n in the first case are basically second half of the second stream and first half of the first stream respectively. So that's why we check if y11 equal to y22, and same goes for while checking y12 is equal to y21. So if both these conditions are satisfied, then distinguisher is convinced that okay, the output was actually from a PRF. So it returns b dash equal to 0. Otherwise, it returns b dash equal to 1. So just like the previous game, if b is 0, then the probability that b dash is 0 is 1. So the game, if b is 0, then it is always true that this condition will be satisfied, that y11 will be equal to y22 and y12 will be y21. So this probability is 1. And what if actually verifier produced truly random functions output, but distinguisher thought that it is from a PRF because it got this condition satisfied in a uniformly random string, that y11 was equal to y22 and y12 was equal to y21. This will happen only this limited number of cases. So among the all 4n output string, y1 is of length 2n and y2 is of length 2n. So total 2 to the power 4n number of combination, and among them this has to be satisfied. So basically you get to choose only 2n number of bits among these 4n bits, and the rest of the 2n is just equal to the other parts. So you basically get 1 by 2 to the power 2n. And thus distinguishing advantage of this adversary is 1 minus 1 by 2 to the power 2n, which is again not negligible. And so we conclude that this construction of fk-x is also not secure. And then comes third construction, g of x is 1 concatenated with kx. So gkx is 1 concatenated with fkx. So how the like if you just see the intuition, it is that the output of gkx will always be always have a leading 1 in the output, right? So this information is can be effectively used by the distinguisher to distinguish output of gkx from a truly random output, right? So intuitively, it is very much clear that this construction is also not going to be secure. So let's just see the what distinguisher does is that seeing the output y for any submitted query input x, it checks if first bit of y is 1. If it is 1, then return b dash equal to 0, and else returns b dash equal to 1. Now, if b is actually 0, of course, y will have a leading 1 in it, and the adversary will obviously return b dash equal to 0. So this occurrence, probability of this occurrence, that b dash is 0 and provided b equal to 0, this is 1. And what if b equal to 1, so y was actually truly random generated string, and then the probability that first bit of y is 1, so that b dash is 0, that is half, because each bit of the uniform random string has the probability of half to be 0 or to be 1. So distinguishing advantage of this adversary is 1 minus half, that is half, which is a constant and of course not negligible. So that's how we conclude that this is also not secure. Oh, sorry. Okay. You could have said that the rejoining, I forgot to share my screen. Okay, I don't know. Okay, let me stop sharing and do it again. Okay. My screen was shared. Okay, I'll just share it. Is it okay now? Padmavati? Okay, yes, you can rejoin. Okay, I will proceed with the discussion. So I hope this third construction is also clear. Oh. So last construction is that gkx is equal to f of fkx of x. So input is x and we use as key f of kx. So whether it is secure or not. So we will basically claim that this is indeed a secure construction of PRF. Intuitively, you can just see that our uh, target is to keep the key K secret, and now and also the key is uniformly random. Now, if the key getting used is fk of x, so fk of x is basically a pseudo random output, so the key can be thought of as a randomly chosen element from key space. So let's see the formal analysis. So we will argue basically that if there is an efficient distinguisher which is able to distinguish the output of fk dash x from a truly random output, then there must exist another distinguisher d which is able to use the output of d dash to distinguish output of f of kx from the truly random output. And as it is already given that f of kx is a secure PRF, so such distinguisher d dash cannot exist. So that's how by contradiction we conclude that the system is secure. So the game is like this. There will be again a verifier, a distinguisher d, and a distinguisher d dash. D will be using d dash, and how that we will see. So let's say d dash generates a query input x, and d passes the query input x as it is to the verifier, and verifier will, as previously, output either the PRF output fkx or a truly random output. So the game between this verifier v and the distinguisher d is like the PRF game uh, for the PRF fkx, and the game between this distinguisher d and the distinguisher d dash is like the game between the PRF game for fk dash x. So you see this part, the communication between the verifier and distinguisher is just submitting the query input x and getting back y, where y can be either fkx or can be tx. Now the job of this distinguisher d is to try to correctly guess what is the value of this bit b, and it uses d dash in a way. So what it does is that it again uniformly randomly chooses a bit b dash from 0 or 1, and if b dash equal to 0, then it basically calculates y dash as f of x with key as y. So it got back y from v, and it uses y as the key and calculates another string y dash. And if b dash is 1, then it just keeps the y dash as y as it is. Okay. And now, what is the view of distinguisher d dash? It submitted a query input x, and it get back an output y dash, such that y dash has the form of f, f of x with key as f of kx, essentially. So d dash is participating in a PRF game for fk dash x, and as we assume first that d dash is able to effectively distinguish fk dash x from truly random function output, so it will output some distinguishing bit b double dash to say whether it is seeing a TRF output or a PRF output. And what now d does is that it sees that if b dash is equal to b double dash, that is, it checks whether d dash is able to guess the bit b dash correctly or not. If d dash guesses correctly, that is b double dash is equal to indeed b dash, then Okay, there is a small mistake here. What distinguisher D returns is actually if D dash is able to correctly distinguish the bit B or not. So if B dash is actually equal to B double dash here, then it will return 0. That is, it will tell the verified that okay, you provided me with PRF output. So this comparison will be actually B dash not equal to B double dash. Okay. Just as we assume that if B equal to 0, then Y will be constructed in PRF way. So this is the bit output will be B dash not equal to B double dash. Okay. So that's how distinguisher D tries to guess the initial bit B0. And as we were saying previously, that the probability that D wins, this distinguisher is able to actually distinguish between PRF and TRF output, that is equivalent to the case that D dash wins. Okay. If D dash is able to distinguish between FK dash X and truly random output, then D will also be able to distinguish between FKX and truly random function output. And so, and we already know that f of kx is secure. So this is a contradiction. No such distinguisher can distinguish the PRF FKX output from truly random function output with non-negligible probability. So we conclude that FK dash X is secure. Otherwise, FKX would not have been secure. So I hope this analysis is clear to you. Okay. So proceeding to the next question, we say that there is PRG which input takes as input n bit string and outputs L bit string. We construct a keyed function fk where fkx is gk XORed with x and use fk to design an encryption algorithm encryption of k. For encrypting L length L length messages. And encryption algorithm is provided as follows. So encryption of M with key K returns a ciphertext which has two parts. First part is some random value R, and then we apply FK on that randomness R, and with that XOR the message M. Okay. So there is a comment about single message ciphertext only attack security, single message CPA security, and multi-message CPA security. So we will see them one by one. So let's analyze what about the COA security. So as you see that it is a randomized encryption algorithm because the value R is chosen every time randomly, and then M is XORed with a pseudo-random string, right? So G of K is a pseudo-random output with seed as K, and with that we XOR some randomness R, so that this whole bit for a fixed message, we run the encryption algorithm multiple times, this R will change and GKs or R will also be changing. So this is equivalent to XORing the message M with some pseudo-random string, just like one-time pad. So this is of course ciphertext only attack secure, because by seeing, so basically what you can do is that you can XOR the first part with the second part and get GK XOR M, but that actually leaks nothing about the underlying message M when you have access to the ciphertext only. So that's how it is secured against an eavesdropper. And about CPA security, so we just provide a counter example here to prove that it is not CPA secure. So in CPA security, what happens is that the adversary has access to an encryption oracle. So it can query with any plain text there. So let's say that the adversary queries with plaintext all 0. So the message is of length L. So L bit string with all 0 is input as query to the encryption oracle, and in response the adversary is able to see a ciphertext which is of the form R, comma zk zor R, zor 0 to the power L. As zoring 0 to the power L with anything gives the original string back. So this is nothing but zk zor R, and also R is available. So the adversary can know the value of zk basically here. So with that information, what it can do is that if the adversary is provided with a ciphertext which is either encryption of M0 or encryption of M1, it can easily say with probability 1, in fact, that whether it is encryption of M0 or M1, because it knows M0 and M1, because in the challenge phase, the M0 and M1, which are provided by the adversary to the verifier, are of its own choice. So M0 and M1 are known to adversary. Adversary has now knowledge of GK. So using that, it can clearly see whether it is seeing GK XOR M0 or it is seeing GK XOR M1. So it is clearly not a CPA secure scheme. And as it is not single message CPA secured, of course, the multi-message CPA security is also not there. So the only valid option here is that this encryption algorithm is single message CPA secure. So here is another question. So let pi, which is a tuple of 3 algorithms, GEN, ENC, and DEC, key generation, encryption, and decryption algorithm. This is a symmetric key encryption scheme. And also consider a variant pi dash, where GEN algorithm is essentially the same, and encryption and decryption algorithm are just variant of the previous one, such that encryption like ENC dash K of M is ENC of K on reverse of M. Reverse of M is nothing but the bit string obtained by reversing the order of bits of M. Okay. Now the decryption is also performed accordingly. That is, you just take a ciphertext, apply decryption on it, and then reverse the output, and you get the plain text back. So anyway, there is comment about whether we can say that if pi is single message COA secured, then so is pi dash. If pi is multi-message COA secured, then so is pi dash. If pi is CPA secured, then so is pi dash. So which among them are true? Anyone would like to comment on that? Okay. So let's discuss. So first, see that okay. Yes, Aditya.
Ma'am, can I ask something? Ma'am,
Yeah.
will we get access to these slides or the recording? Because last time, like last for
Yes,
week 1 week.
I heard actually in the beginning of this session only someone asked. So actually you were supposed to get the access to them. I don't know, NPTEL authority did not mail you. So I actually can share this YouTube link with you. So for the previous session, the last week session, I can okay. Just
Can
let
you
me
share?
finish. Let me finish today's session. I will share the YouTube link. Okay, for
Thank you,
previous
ma'am.
session. So getting back to what we were discussing, so we were given that pi is COA secure, and let's assume that pi dash is not COA secure. So what happens is that then adversary is, so by saying that pi dash is not COA secure, we mean that the adversary is able to learn extra information about the distribution of underlying plain text. And what is the underlying plain text here? It is distribution of reverse of M. But this knowledge, if you know the distribution of reverse of N, that of course leads to gaining information about distribution of M as well. because reversing is just that sequence of bits are reversed, nothing else. So basically, that's how we can say that it is so pi dash is actually COA secure. If it is not, then that will imply that pi is also not COA secure, but it's already given that pi is COA secure. So that's a contradiction, and we conclude that pi dash is COA secure. And about CPA security, we just consider this game. So there is verifier, there is adversary, and there is another adversary A dash, which is able to, let's say, attack the CPA security of the scheme pi dash. And if such adversary is present, so attacking means here that able to say, given a challenge ciphertext CB, whether it is encryption of M0 or M1. If A dash is able to guess the bit B correctly, then using A dash, there must be another adversary A which can attack the crypto system pi, and it can guess the value B in this case. So I did not write this like choice of B from 0, 1 field and then encrypting MB. So you already know that. So let's say that A dash submits a query input MI as the CPA game proceeds. So in the CPA game, there is query phase and there is a challenge phase, and there might be post-challenge query phase also. So for now, we consider just the pre-challenge query phase. So there is query input MI, and what A does is that it just reverses this MI and submits to verifier. Verifier in response provides A with CI, which is encryption of this reverse of MI. And A just forwards this CI to A dash. So in the view of A dash, it sees encryption according to the scheme pi dash, that is encryption of reverse of M using key K. And now A dash submits two messages of its choice, M0, M1, and A forwards them as reverse of M0 and reverse of M1 to verifier, and verifier gives it back some CB, anyone encryption of any one of them, and CB is exactly forwarded as it is to A dash. And now A dash outputs the distinguishing bit B dash, and whatever is the output of A dash, A just forwards this thing to verifier. Now see that if A dash wins pi dash with non-negligible probability, by pi dash I mean the game, this game of CPA security for the scheme pi dash. If A dash wins in that with negligible probability, A wins pi with non-negligible probability. So okay, if it ends, please join again. Okay, so that will imply that pi is not CPA secure. So this is a contradiction, and thus we conclude that pi is CPA secure. That implies pi dash is CPA secure. Okay. Okay. So proceeding to the next question. Consider an encryption scheme where encryption is applied twice on the plaintext. To make the system more secure, consider a basic encryption scheme pi. Again, a tuple of Jane, ENC, and DAC three algorithms, and then modify it to design pi dash equal to Jane, ENC dash, DAC dash, such that encryption is just but double, nothing but double encryption on M. That is encryption M use encryption dash KM is encryption of K, comma encryption of K comma. Okay. So encryption of M is encrypted again using the same key K. Now analyze pi dash to answer the following. So describe the decryption algorithm and correctness of pi dash. This is very obvious. Decryption algorithm is nothing but again decrypting it twice. First time you decrypt C and you get first layer encryption of M with K, and you decrypt it again to get back the plain text M. That is trivial. Next question is check whether IDAS is int CPA secure provided that I is int CPA secure. So just like the previous example, we again resort to this similar kind of game between verifier adversary and adversary dash. And so first part of the game between verifier and this adversary A is nothing but the replica of CPA security game for the scheme pi, and the right hand side part between A and A dash is nothing but the CPA security game going on for the encryption scheme pi dash. How it is how is it going on? So it is like A dash submits query MI, some query plain text, and A just forwards it to verifier as it is. And in response, first A gets back CI, which is encryption of MY with K. And before forwarding the answer to A dash, it does another query. So for each query from A dash, A has to do 2 queries for each MI because it needs to forward double encryption to A dash. So A basically again submits this CI as the plain text query to verifier, and in response it gets encryption of CI using key K. And now it forwards this CI dash to adversary A dash. So in view of adversary A dash, the game is going on as it is, that encryption dash KM is equal to encryption of K of encryption of K. Okay. So this is how the query phase is going on. And now in the challenge phase for A dash, it submits two challenge, like two plain text input M0 and M1. And A forwards it to V as it is in the first step and gets back CB equal to encryption of MB with key K. So this is the challenge ciphertext for the adversary A. Now, let's assume that A starts the post-challenge query phase now by querying the verifier V with plaintext query input as CB itself. And it gets back CB dash, which is encryption of CB with key K. And now it forwards CB dash to A dash. And for A dash, this CB dash is the challenge ciphertext. Notice that for A, CB is the challenge ciphertext, but for A dash, CB dash is the challenge ciphertext. And here the query for encryption of CB is belonging to the post challenge query phase here. But here there is no post challenge query phase. A dash directly outputs the distinguishing bit B dash to say that which one among M0 and M1 was encrypted in CB dash. And we assume such A dash exists, which is able to non-negligibly distinguish the encryption of M0 from encryption of M1. And A dash is just returning the same bit B dash equal B double dash equal to B dash to the verifier. And again we just by contradiction say that if A dash exists, then such adversary A also exists, which is able to distinguish ciphertext of M0 from ciphertext of M1 effectively, that is with non-negligible probability. But we already know that the pi is CPA secure scheme. So CPA security has to be ensured for pi dash as well. So we conclude that pi dash is CPA secure. And coming to the eavesdrop security in presence of eavesdropper. So what we provide is a counter example to say that IDAS is not necessarily EAV secure. So let's consider one-time pad as EAV secure scheme, which is a known EAV secure scheme. So let's say pi is nothing but OTP. Now, the way we design pi dash, just notice that encryption according to OTP, which is pi in this example here, encryption of K of M is like M is joined with K. However, if pi dash is designed as encryption of k of m, then it basically does k XOR m, which is returning m itself. So the ciphertext is nothing but the plain text itself, and obviously just any eavesdropper which is observing the communication channel and sees the ciphertext just gets to know the plain text without any effort. So this is very much not EAV secure. So pi is EAV secure does not imply that pi dash is EAV secure here. Coming to the last problem. So FB and FBA length preserving PRA for the following construction of a key function f dash, where key space is n length binary string and the input space is n-1 length binary string, and the output is 2 n length binary string. So there are two proposed construction of f dash, and we need to comment on the security of f dash, whether f dash is actually secure PRA or not. Okay. If the meeting ends, please join again the same link. So let's see the first one, which says that fk dash x is fk of 0 concatenated with x concatenated with fk of 1 concatenated with x. So basically, as you see, fk takes as input a n length string, but fk dash takes as input n-1 bit length string. So we design the game in this way that whenever the distinguisher d dash submits a query plain text x, the distinguisher d first generate x1 as 0 concatenated with x and sees the output from verifier, where verifier can output either a PRF output or a truly random output. And it again submits another query x2, which is 1 concatenated with x2 and sees the output y2. And then this y1 concatenated y2 completely is given back to d dash as output from this d. So again, the left hand side game is according to the construction of fk, and the right hand side game is according to the construction of fk dash. And if d dash is able to win the game, that is able to distinguish whether y is generated from fk dash or from uniformly random string, then d is also able to distinguish between the output of fk from a truly random function. And that's how we just conclude that fk dash is secure by contradiction, just as in the previous example also you have seen. So this is the last problem. So here another construction of fk dash x is given as fk of 0 concatenated with x concatenated with fk of x concatenated with 1. So this is very interesting example actually. So we will actually say that fk dash is not secure. Although this looks very similar with the previous example where we did fk of 0 concatenated with x concatenated with fk of 1 concatenated with x, but just by reversing this last part, doing fk of x concatenated with 1, this makes the PRF insecure. So how? Let's say in the first query input, the adversary submits the query input as 0 to the power n-1. So what happens is that the distinguisher actually sees fk of 0 to the power n. So 1 0 is leading to this x1. So 0 to the power n concatenated with, in the second part, 0 to the power n-1 is concatenated with 1. And assume that in the next query input, the adversary or the distinguisher submits the query input as 0 to the power n-2 and 1 1 at the end. And what happens? So the distinguisher now sees as output of fk dash x, fk of 0 into the power 1 and 1 trailing 1 concatenated with fk of 0 to the power n minus 2 and 2 trailing 1. So if you see that this part and this part are exactly same, so just looking at the output y1 and y2 corresponding to the input x1 and x2, if it compares the second part of the first output string y1 and first part of the second output string y2, and if they are equal, it can use that information to say that whatever output it is seeing is from a PRF or from a truly random function. So if it is satisfied that these two strings are equal, that implies that distinguisher will output b dash equal to 0. That is, it says that the output is from PRF. Otherwise, it says that the output is from TRF. And as usual, probability of b dash equal to 0, given that b equal to 0 is 1. And probability of b dash equal to 0, given that b equal to 1, that is actually the string was truly random string. So that will be the total number of possible string of length 4n, because y1 is of length 2n, y2 is of length 2n, so total 4n number of bits. So denominator has to be the power 4n, and then as these two strings are essentially has to be equal, so like that possible string is to the power 3n. So we get distinguishing advantage as 1 minus 1 over 2 to the power n, which is not negligible. So basically we show that fk dash is distinguishable from a truly random function output. So this is not a secure PRF. Okay. So that concludes today's problem solving session. So I will just share in the chat box here the YouTube link. Just give me 1 minute, okay? Okay. Thank you, everyone. So I am ending this session. Okay. Thanks for attending.